What if one ordinary afternoon inside a quiet monitoring station captured the first clue that something from another star had already reached Earth and nobody noticed? The moment did not look dramatic. There were no alarms echoing through control rooms, no emergency briefings, no urgent headlines. Instead, it started with a routine shift, a cup of coffee, and a data screen that had been checked hundreds of times before. The location was a remote U.S. government sensor facility positioned at 72 degrees north latitude and 38 degrees east longitude. Its purpose was simple but critical: monitor the upper atmosphere for ballistic signatures. These systems constantly track high-speed objects entering Earth's atmosphere, primarily to detect missile activity or natural meteors. On February 12, 2025, at exactly 2:23 p.m. UTC, a duty analyst sat at his workstation conducting a routine telemetry review. Nothing about the day suggested that anything unusual was about to appear. Two monitors glowed in front of him. One displayed atmospheric tracking data, the other held system logs scrolling slowly forward. His coffee sat to the left of the keyboard. It was the kind of shift that rarely produced surprises. Flag a signal, log it, move on. Repeat the process hour after hour. Then the sensors triggered. An object had entered the atmosphere. At first glance, it appeared to be another routine meteor detection, but the velocity reading made the analyst pause. The system measured the incoming speed at 72.4 kilometers per second. He checked the calibration. Then he checked it again. The number remained unchanged. To make sense of it, he looked up at the velocity threshold chart pinned just above his workstation. Every analyst knew that chart by memory. It listed the maximum speeds expected from objects bound to our solar system. At Earth's distance from the Sun, the escape velocity, the speed required to break free from the Sun's gravitational pull, is 42.1 kilometers per second. Anything moving faster than that is not orbiting the Sunday. It is passing through. The object in the sensor data was traveling more than 30 kilometers per second faster than that limit. That meant it was not simply a meteor drifting within the solar system. It had entered our atmosphere carrying positive heliocentric energy, the defining signature of something that originated outside the Sun's gravitational influence. In other words, it had come from interstellar space. The analyst followed protocol. He flagged the event, logged the measurement, and picked up the phone to report the anomaly. Within 6 hours, the impact was recorded in the NASA Center for Near-Earth Object Studies Fireball database. Officially, it was categorized as a routine atmospheric entry. No announcement was issued. No press briefing followed. The entry labeled Barents Sea Event was cataloged, time-stamped, and quietly archived. The world never noticed. 14 months later, a group of researchers began examining that database entry in detail. Using 1 million Monte Carlo simulations, statistical models designed to test every possible variation in measurement uncertainty, they reconstructed the object's trajectory again and again. Their calculations accounted for atmospheric drag, Earth's rotation, gravitational influences from planets, and instrument margins of error. The results were not ambiguous. Across all 1 million simulations, every possible trajectory produced the same conclusion. The object's heliocentric energy remained positive, unbound, interstellar. By the time those results were confirmed, the analyst's forgotten coffee had long gone cold. Yet the object he recorded that afternoon carried a detail that made the event far more significant than anyone initially realized. It arrived exactly 139 days before another object was detected entering the solar system, a much larger one known as 3I Atlas. 139 days. That number may seem like a coincidence, but once you start looking deeper into the data, the pattern becomes impossible to ignore. Because this is not just the story of a meteor strike, it is the beginning of a forensic investigation into 4 separate interstellar objects that struck Earth over a period of 12 years. Their timing lines up, their compositions raise questions, and the physics behind their trajectories forces us to confront a possibility that scientists have been hesitant to discuss openly. By the time we reach the end of this investigation, one thing becomes clear: the universe may have been sending us signals long before we realized we were receiving them. And to understand why that possibility matters, we first need to examine the physics behind escape velocity and why exceeding it changes everything. If you want to uncover what the data reveals next, make sure to subscribe and stay with me, because the deeper we go into this investigation, the more difficult it becomes to dismiss what the numbers are telling us. To understand why that single velocity measurement mattered so much, you first have to understand the basic physics that governs movement inside our solar system. Every star creates a gravitational well, an invisible region where its mass bends space and controls the motion of surrounding objects. Planets, asteroids, and comets all move within this gravitational structure, following paths that remain tied to the star that holds them. As long as an object stays below a certain speed, it remains trapped in that gravitational field. For our Sun, that critical limit at Earth's distance is 42.1 kilometers per second. This number is known as the solar escape velocity at 1 astronomical unit. Any object traveling slower than that remains gravitationally bound to the Sunday. It might orbit for millions of years, it might swing past the planets in long elliptical paths, but it will never leave the system entirely. It is part of the Sun's family of objects. But once something exceeds that speed, the situation changes completely. An object moving faster than the escape velocity carries what physicists call positive heliocentric specific energy. Instead of orbiting the Sun, it simply passes through the solar system. It is not captured. It does not belong here. It arrived from somewhere beyond the Sun's gravitational reach and will eventually continue on its way into interstellar space again. For decades, astronomers suspected such visitors must exist. After all, stars constantly eject debris during planetary formation and stellar evolution. Over billions of years, that debris drifts between star systems. But until recently, scientists had never confirmed one of those travelers directly. That changed in 2014. On January 8th of that year, an object slammed into Earth's atmosphere near Papua New Guinea at an astonishing 60 kilometers per second. That speed alone immediately placed it among the fastest meteors ever recorded. In fact, it became the highest impact velocity in the entire meteor observation catalog. The object was later designated IM-1. At the time of impact, the data came from U.S. Department of Defense sensors. For several years, the measurements remained classified, making independent verification difficult. But after a formal petition by researchers requesting confirmation, U.S. Space Command officially declassified the velocity data in 2022. Their statement confirmed what the numbers had already suggested. IM-1 was interstellar. It had traveled through space for unknown distances before colliding with Earth's atmosphere. When it entered at extreme speed, the intense heat of atmospheric friction caused the object to vaporize almost instantly. The original body disappeared, leaving only microscopic remnants scattered across the ocean. But those remnants did not vanish completely. In June 2023, a research expedition returned to the impact location in the Pacific Ocean. Using a specialized magnetic sled dragged slowly across the seafloor, scientists collected hundreds of tiny metallic droplets embedded in the sediment. These particles were called spherules, each less than a millimeter wide, formed when the meteor melted and condensed during atmospheric entry. In total, The team recovered around 850 of these metallic spherules. Back in the laboratory, researchers performed detailed chemical analysis on the samples. What they found immediately raised eyebrows across the scientific community. The composition did not match any known class of meteorite in existing catalogs. The spheres showed unusual enrichment in beryllium, lanthanum, and uranium. More importantly, the ratios between those elements did not align with any natural nucleosynthesis processes known to occur inside stars or planetary systems. Meteorites normally reflect the chemical environment of the solar system where they formed, but these particles did not resemble material produced anywhere within our system. Even more intriguing were the isotopic signatures embedded in the samples. Those signatures suggested the material had been exposed to billions of years of cosmic ray bombardment, something that happens primarily in the vast emptiness between stars. Taken together, the evidence pointed toward a clear conclusion. This was not just unusual material. It was categorically foreign. Then, 3 years later, another event occurred. On March 9, 2017, a second high-speed object exploded in Earth's atmosphere above the North Atlantic Ocean. Its velocity measured 59.8 kilometers per second, once again exceeding the solar escape threshold. The explosion released energy equivalent to 3 kilotons of TNT at an altitude of about 31 kilometers. Researchers labeled this second object M2. 6 months later, something remarkable happened. On October 19, 2017, the Pan-STARRS telescope in Hawaii detected the first large interstellar object ever observed passing through our solar system. Astronomers named it Oumuamua. At the time, the timing between the atmospheric impact and the arrival of this interstellar visitor was noticed, but most researchers dismissed it as coincidence. However, once you place those events alongside the newer data, including the 2025 Barents Sea impact, the pattern begins to look very different, and that is exactly where the investigation becomes much more complicated. If you're following this investigation closely, stay with me, because in the next part, we examine 2 more interstellar impacts and the statistical pattern that makes coincidence harder and harder to defend. Now let's place all of these events on a timeline, because once the sequence becomes visible, the pattern starts to look far less random than it first appeared. After the confirmed interstellar impacts of IM-1 in 2014 and IM-2 in 2017, researchers turned back to the global fireball databases, searching for additional objects that might have slipped past unnoticed. These databases record thousands of atmospheric entries every year, but most of them are ordinary meteors moving at speeds that clearly place them inside the solar system's gravitational limits. What scientists were looking for were objects moving faster than the sun's escape velocity, the same signature that had revealed IM-1 and IM-2 as interstellar visitors. Using refined measurement techniques and updated uncertainty models, researchers began reanalyzing the data more carefully than ever before. This deeper search revealed 2 additional events that stood out immediately. The first occurred on July 28, 2022, when an object designated C-NEOS 2022 struck Earth's atmosphere above the eastern tropical Pacific Ocean at approximately 8:17 UTC. The measured velocity was not just above the solar escape threshold, it exceeded it by 8.7 standard deviations, a level of certainty that leaves very little room for measurement error. Statistically speaking, that level of deviation means the probability of the object actually being bound to the solar system is extremely small. The second event was the one that had quietly entered the database from the Barents Sea on February 12, 2025, the same entry logged by the analyst during that routine afternoon shift. This object, labeled C-NEOS 2025, exceeded the solar escape velocity by 5.5 standard deviations, once again pointing strongly toward an interstellar origin. To test these findings, scientists ran 1 million Monte Carlo simulations for each event. These simulations systematically adjust every uncertain parameter, measurement, noise, atmospheric drag variations, Earth rotation, gravitational influences from nearby planets, and calculate possible trajectories under all reasonable conditions. If even a small fraction of those simulations produce a bound orbit, then the interstellar conclusion becomes weaker. But that is not what happened. Across every single simulation, the trajectories remained unbound. Both objects were traveling too fast to belong to our solar system, and then researchers noticed something that changed the entire conversation. The Barents Sea object from February 2025 arrived 139 days before the discovery of a new interstellar visitor entering the solar system, an object astronomers later named 3I Atlas. The timing immediately reminded researchers of an earlier sequence. Back in 2017, the atmospheric impact of IM2 had occurred 6 months before the detection of Oumuamua, the first confirmed interstellar object ever observed passing through our planetary neighborhood. 2 atmospheric impacts. 2 later discoveries of large interstellar visitors, both separated by several months. At first glance, the pattern might still appear coincidental, but scientists began applying statistical models to determine how likely such alignments would be if they were purely random. Using Bayesian probability frameworks, researchers evaluated the chances that the 2017 and 2025 correlations happened independently by coincidence. The result was surprising. The probability of the timing being random came out to roughly 6%, which means the probability that the correlation is not random sits at approximately 94%. In most scientific fields, a probability that high would immediately motivate further investigation. It would trigger funding proposals, new experiments, and coordinated observation campaigns. When a pattern shows up repeatedly in data with that level of statistical weight, scientists normally treat it as the beginning of a new hypothesis worth testing. But in this case, the response was different. Instead of launching major research efforts, the proposals exploring this pattern encountered resistance. 2 separate submissions attempting to analyze the phenomenon more deeply were rejected. The explanation was not that the calculations were incorrect. The methodology itself passed review. The issue, according to reviewers, was the interpretation. Some researchers had begun applying a theoretical perspective sometimes called the Kaku lens, a framework built from concepts in string theory and the Kardashev scale, which classifies civilizations by the amount of energy they can harness. Within that framework, an advanced technological civilization capable of traveling between stars would likely deploy small reconnaissance instruments ahead of larger vessels. From Earth's perspective, those instruments would not appear as obvious spacecraft. They would appear as exactly what the data already showed: small objects, extremely fast, arriving ahead of larger interstellar visitors, and sometimes striking a planet's atmosphere. Whether that interpretation is correct remains an open question, but the pattern in the data timing, velocity, and trajectory cannot simply be ignored, because once those pieces are placed together, they begin to suggest something that goes far beyond a few isolated meteor impacts. And in the next part of this investigation, we will examine the physical evidence that could confirm or completely disprove this extraordinary possibility. If the pattern in the data truly means something, then the next question becomes unavoidable. Where is the physical evidence? Numbers and trajectories can suggest possibilities, but science ultimately depends on material proof. In the case of these interstellar impacts, the most important clue may still be sitting exactly where it landed. The recovery site for the CNEOS 2025 event in the Barents Sea is not some unreachable location buried miles beneath the ocean. The coordinates are known with reasonable precision, and the depth at the impact point is about 230 meters. In oceanographic terms, that is relatively shallow water. The seabed in that region consists largely of soft sediment, which means any surviving fragments from the object would likely be resting only slightly buried beneath the surface. Even more important is the method scientists already know how to use to retrieve them. In 2023, the expedition that searched for fragments of IM-1 near Papua New Guinea used a device called a magnetic sled. This tool is dragged slowly across the ocean floor while powerful magnets collect metallic particles embedded in the sediment. That simple technique successfully recovered hundreds of microscopic spherules from the IM-1 impact site. Those tiny droplets ultimately became the first physical samples ever collected from a confirmed interstellar object. The same approach could easily be used again in the Barents Sea. With modern positioning systems and existing ocean survey equipment, a search expedition could scan the impact region with high precision. The technology already exists. The coordinates are known. The depth is manageable. From a purely logistical standpoint, the recovery mission would be entirely achievable. Because of that, researchers prepared a formal expedition proposal and submitted it to the National Science Foundation. The proposal went through standard peer review, evaluated by 3 independent scientists. All 3 reviewers gave the project strong scores. In fact, the proposal cleared the funding threshold required for approval. Yet, despite meeting the scientific criteria, the mission was rejected. The official explanation stated that there was insufficient evidence that recovered material would provide scientifically significant information beyond existing meteorite collections. For many researchers following the case, that decision raised immediate questions. Interstellar material is extremely rare. In fact, confirmed samples are almost non-existent. The fragments recovered from IM-1 already demonstrated chemical properties unlike anything in the current meteorite catalog. Recovering additional samples from another confirmed interstellar impact would seem, at least on the surface, to be an obvious scientific opportunity. Still, the decision stood. No expedition was funded. Meanwhile, the larger pattern in the data continued to develop. When scientists began calculating how frequently these interstellar objects should appear based on the known impact events, they arrived at a number that surprised almost everyone involved. Using the observed rate of impacts and the estimated detection sensitivity of current monitoring systems, researchers derived an approximate population density of 8.4 million interstellar objects per cubic astronomical unit. To visualize that number, imagine a cube of space measuring the distance from the Earth to the Sun on each side. According to the calculations, that volume of space could contain millions of small interstellar objects, each roughly 1 to 1.5 meters across. Within Earth's orbital region alone, the estimated population climbs to around 35 million objects. That density creates an immediate problem for existing astrophysical models. Current theories about how stars eject material into interstellar space simply cannot produce that many objects. Stellar winds, supernova explosions, and planetary formation debris all contribute material to the galaxy, but even when those processes are combined, the predicted density remains far lower than what the impact data suggests. In fact, the difference is enormous. The mass implied by the observed impact rate inside Earth's orbit reaches roughly 100 trillion metric tons of interstellar material. For comparison, The entire asteroid belt between Mars and Jupiter, an enormous region filled with billions of rocky bodies, contains only a few percent more mass than that. In other words, according to the calculations, a significant fraction of the asteroid belt's total mass could be represented by interstellar objects drifting within Earth's orbital region. That scenario forces scientists into an uncomfortable position. Either the models describing how stars eject material into the galaxy are wrong by a factor of 1,000, or the objects we are detecting are not randomly scattered debris at all. And once that possibility enters the discussion, the interpretation of these impacts begins to change dramatically. Because if these objects are not simply drifting through space by chance, then their presence near Earth might have a very different explanation. And that is where the investigation takes an even deeper turn. If you want to follow where the physics leads next, stay with me, because in the next part we examine the two possible explanations scientists are now forced to consider, and one of them challenges our entire understanding of how interstellar space may actually be used. At this point in the investigation, the mathematics leaves scientists with only two possible explanations, and neither one is comfortable. The first possibility is that our understanding of the galaxy itself is fundamentally wrong. The second is that the objects appearing in these impact records are not simply random debris drifting through space. To see why the problem becomes so serious, consider how interstellar material is normally expected to behave. The Milky Way galaxy contains somewhere between 100 billion and 400 billion stars. Over billions of years, those stars constantly eject matter. Stellar winds push particles outward. Supernova explosions scatter heavy elements across vast distances. During planetary formation, leftover debris is often thrown out of a system entirely through gravitational interactions. All of these processes release material into interstellar space. Astrophysicists have spent decades building models that calculate how much debris should exist between stars based on those mechanisms. When the numbers from stellar evolution, galactic dynamics, and nucleosynthesis are combined, they produce a fairly consistent prediction for the density of interstellar objects drifting through the galaxy. But the population density implied by the four impact events we've been examining is dramatically higher. The calculations suggest a concentration of interstellar objects roughly 1,000 times greater than those models allow. That gap is far too large to ignore. If the numbers are correct, then either our entire understanding of how stars eject matter into space must be revised, or the objects detected near Earth are not part of a random galactic background at all. Those are the only two exits from the mathematical corner created by the data. The first option would require rewriting major sections of astrophysics. Scientists would have to reconsider how much mass stars lose over their lifetimes, how efficiently supernova explosions distribute material, and how gravitational interactions scatter debris across the galaxy. Such revisions would ripple through nearly every model used to describe galactic evolution. The second possibility leads in a completely different direction. If the objects are not randomly distributed, then something may be concentrating them near specific locations. That idea brings researchers into contact with several theoretical frameworks that have existed mostly on the edges of scientific discussion. Among them are directed panspermia, von Neumann probe architectures, and large-scale technological deployment models based on the Kardashev scale, which classifies civilizations according to their ability to control energy. Within those frameworks, a highly advanced civilization capable of operating at a Type 2 or Type 3 level would possess enormous technological resources. Instead of launching every exploration device individually from a home world, such a civilization might deploy networks of small, self-sustaining probes across interstellar space. Some models even suggest the possibility of self-replicating machines capable of spreading gradually from star system to star system. In that scenario, the density of objects detected near Earth would not represent random debris drifting through the galaxy. Instead, it could represent a localized concentration of devices positioned near a target of interest. And Earth could be that target. The chemical evidence recovered from the IM-1 spherules adds another layer to this discussion. Laboratory analysis revealed unusual ratios of beryllium, lanthanum, and uranium, elements that normally form under very specific astrophysical conditions. The production of those elements requires extremely intense neutron flux environments conditions typically found during events like neutron star mergers or certain types of supernova explosions.